Swayam Prabha. Digital India. Educated India.
Now, we have been talking about stream function and vorticity in the last few lectures. I thought what would be nice is if we can actually solve a couple of problems to illustrate the ideas and the concepts, okay. And with that in mind, let us do some problems and then we will see. So, consider the uniform flow, okay, in the x direction. What is the meaning of uniform flow? Velocity is u equal to u naught everywhere, okay. The velocity is u equal to u naught, and I want to basically try and this of course if u is equal to u naught, it does not change with x. So, we expect that this is a one dimensional flow, okay, and I want to calculate, find psi the stream function and phi the potential function for this problem. Since the velocity is given, so d psi by dy must be equal to u naught. This is the x component of velocity, and in terms of stream function, this is Vx or u, which is the x component of velocity, is given like this, okay. So, now I want to calculate the stream function. So, stream function is given as integrate this thing u naught y plus some function of x, okay. And what do I do? I need to find out why is this a function of x, because this is partial with respect to y, I get a function of x. I differentiate this with respect to x. What do I get? D psi by dx equals g dash of x, and this must be equal to minus Vy by definition of the stream function. And because this flow is one dimensional, is by definition of the stream function d psi by dx is minus Vy, and because there is no velocity component in the y direction, that is 0. So, that means g dash of x is, and this derivative is a total derivative d by dx, okay. So, this implies g of x equals constant, okay. Now, if I want to plot the stream functions, so psi equals u0 y plus a constant c, that is my stream function. So, I want to draw my streamlines, okay. How are the streamlines defined? The streamlines are defined such that psi is constant on the streamline. So, when I put psi equal to constant, put psi equals constant along the streamline, what do I get? U naught y equals some constant for the psi minus the c, okay. So, basically what I am trying to tell you is the streamlines are all going to be y equal to constant, or y equal to constant means lines that are parallel to the x axis. So, streamlines are parallel to the x axis. I mean, that is possibly common sense, right. I mean, the one dimensional flow, streamlines were parallel to the x axis, and therefore nothing new. You expected the streamlines to be parallel to the x axis, okay. So, because streamline is defined as one where the velocity is going to be tangential to the streamline. So, therefore, the streamlines are parallel to the y axis. Okay. Now, what I want to do is I want to find the potential function. Okay. So, for the potential function, how is the potential function defined? Vx, V is given as gradient of phi, or in other words, Vx is equal to d phi by dx, Vy, the y component of velocity is d phi by dy. Vx is, for our problem, Vx is u naught. Okay. So, d phi by dx is equal to u naught, or phi equal to u naught x plus, again I am integrating in the x direction, this could be some function of y. Is this clear? I am integrating this, I get that. Now, how do I find this arbitrary constant which is the function of y? I find that by differentiating this with respect to y. So, Vy which is 0 equals d phi by dy plus g dash of y. This implies g of y is a constant. Okay. So, point I am trying to make here is phi is u naught x plus some constant c. Okay. Now, what are the lines along which, what are the surfaces, the lines along which phi is constant? So, if I put phi equal to constant, implies u naught x equal to this constant, what are the constant I am taking, minus c. Okay. So, the potential lines are going to have x as constant, which means they are lines that are parallel to the y axis, because x is constant along the isopotential surfaces. Okay. There are surfaces along which phi equal to constant, and these are parallel to the y axis because x equals constant. That is what I am getting from here. I obtain x is constant along the surfaces for which potential is constant. Okay. So, basically what we have is a flow field where the stream functions, this is psi equal to constant and phi equals constant, these are phi equals C1, this is psi equal to constant. So, in this particular problem the streamlines are all parallel to the x axis and the potential lines, isopotential lines along which the potential is constant are parallel to the y axis. Okay. So, you see that the potential lines, the isopotential curves are perpendicular to the streamlines. Okay. So, that is the first thing you observe. That makes sense because the gradient in the potential is the one which is driving the flow. Okay. Now, what I want to do is this property a general property of these isopotential curves being perpendicular to the streamline, or is it only specific to this flow field? That is the question. Okay. So, what I want to establish is that the isopotential curves are going to be perpendicular to the streamlines at every point, okay, if there is a potential function. Okay. So, basically the isopotential curves in the above problem are perpendicular to the streamlines. Okay. Is this always true? That is the question. So, we go back to this definition of psi equals constant on a streamline. So, d psi equals 0, which is d psi by dx plus d psi by dy along the streamline. Okay. So, the tangent at every point, the tangent on the streamline is given by dy by dx, which is dy by dx, which is minus d psi by dx divided by d psi by dy. Okay. What have I done? I have just taken this to the other side. I wrote dy by dx as minus d psi by dx by this thing, and this you remember is nothing but vy by vx, because this is how we define the velocity in terms of the stream function. Okay. So, this is calculus, and this, up till here is calculus. Then I said this is how I define my stream function, and I bring my fluid mechanics inside here. Now, if phi is constant on a surface, again d phi is 0, which is d phi by dx plus d phi by dy. So, along this surface dy by dx, so this is dy by dx along psi equals constant. This is the tangent along the line where psi is constant. So, what is dy by dx along the curve where phi is equal to constant? This is minus d phi by dx divided by d phi by dy. And if you remember, we define velocity as equal to gradient of phi. So, this is nothing but minus Vx by Vy. d phi by dx is Vx, d phi by dy is Vy. Okay. This is, so at any point in the space you can calculate dy. If there is a potential constant potential curve, the dy by the tangent is given by this. If there is a streamline going through it, the tangent is given by this. Clearly these two are perpendicular to each other, because the two slopes, when you take the product you get minus 1. Okay. So, basically what I am trying to tell you is, this particular thing is a general property for any flow field, as long as potential exists, as long as the 2D flow stream function exists. So, dy by dx where psi equals constant multiplied by dy by dx or phi equals constant equals minus 1. So, isopotential lines are perpendicular to streamlines. As long as phi and psi are defined. Okay. So, basically the point is, I mean they are all interconnected, the potential, the stream function, velocity field. So, given one, you can go from one to the other, and then you can find all of them as long as they all exist. Okay. Now consider the Kuwait flow, one dimensional problem. Okay. This is again a one dimensional problem, u equal to 0 here, u equal to u naught at the top surface, and you have already solved this problem and you get a steady state profile like this. So, Vx is equal to u naught y, okay. Flow between two parallel plates, lower plate is stationary, upper plate is moving at a constant velocity, and what is established is this thing, there is no pressure gradient. I want to repeat whatever I did earlier for this particular case, okay. So, Vx is u naught y, Vx is nothing but d psi by dy, Vx equals d psi by dy, and that is equal to u naught y, correct. The distance between the plates is 1, distance between the plates is 1. I am allowed to make some mistakes, not all the time, okay. u naught y, okay. So, take the distance between the plate as 1. So, now I need to find psi. In general, there will be a y by h or y by d, the distance between the plates, but keep life simple. So, I want to find my stream function psi, I will get u naught times y square by 2 plus a function of x. So, the distance between the plates is 1, I am okay, right. So, this is my stream function. Again, in this problem there is no velocity in the y direction, right. So, what is this thing that we get? So, Vy is 0, which means d psi by dx implies d psi by dx is 0, which means f dash of x is 0 or f of x equals constant. Let me call it k, okay. So, basically I am trying to tell you psi is of the form u naught y squared by 2 plus a constant k. I want to now, so basically given the velocity field I have calculated my stream function, streamlines. So, along the streamlines basically some parabola kind of thing you are getting, y square equal to constant. I want to find the potential function now, okay. So, I want to find the potential function, find the phi for this problem. So, how do I find phi? Given the velocity field, so u naught y is d phi by dx, right. Vx is the x component of velocity field, in terms of potential it is d phi by dx, that must be equal to u naught y. So, now phi is equal to u naught xy plus some function of y, and what is d phi dy is equal to u naught x plus g dash of y, okay. This is the velocity component in the y direction, this is the velocity component in the y direction, and you know in our problem the velocity component in the y direction is 0. So, that means this is 0. So, basically what we are trying to, so you have something like a contradiction here, okay. You cannot find what is this g dash of y here, because this is a function of y, which is a here is a function of x, okay. So, you can't really calculate dg by dy as minus u naught x and this is a function only of y, this is a function of x, right. The basic assumption is this is a function of y. So, I have a function of y here, I have a function of x here. So, I have a problem. Okay. So, we have a function of x equals a function of y, and so this is inconsistent. So, there is a problem here, and what is the problem? The problem is my flow will have a potential function only if it is irrotational. Okay. I need to check if my flow field is irrotational, which means omega, the curl of V has to be 0. Okay. So, I want you to check that. I want to check the is my, because only if my flow field is irrotational I will have so this problem may be because my flow field is not irrotational. Okay. What I mean by that is the curl of V 0, because I told you only if the curl of V is 0 I can have a potential function, V can be written as gradient of phi. So, is curl of V 0. So, you do that I j k d by dx d by dy d by dz, and you have the x component of velocity, right, which is u naught y 0 0. Okay. We calculate this, the curl of V is you get I multiply, because there is no change in the z, 0 minus j times 0 plus k times what? Minus u naught. Okay. So, this is just calculating the determinant of the matrix, and you find that the curl of V is not equal to 0, and therefore, flow is not irrotational. Okay. And therefore, phi does not exist here. Okay. So, point is, and omega is not equal to 0, there is a vorticity associated with it, curl of V is omega, right. So, that is basically the point. So, the flow was actually one dimensional, but because it is a subset of 2 dimensional I can get my streamline, but I cannot get my potential function in this case because the potential function does not exist. Okay. So, so that is the reason when I was trying to find the potential function I could not find it. Okay. Because I can't satisfy this condition that d phi by dy must be 0, Vy is 0, I could not get that because it has to be true for all x and y. Okay. My flow field is such that Vy was 0 for all x and y, and this can't be satisfied. So, and the problem was, so what the point is, you may say, look, the streamlines are all pointing in the x direction. So, it looks like all, the velocity field is all linear, I mean in the sense all the particles are going in the same direction. So, where is the question of rotation? So, the the particles themselves are not rotating, they are all moving, but if I were to put some small needle here, this guy will go faster, this guy will go slower, and that needle is going to rotate because of the difference in the velocities. So, by looking at the flow field, you cannot conclude whether the flow field is irrotational or not. That is the point I am trying to make. So, co-ed flow may look irrotational because all the streamlines are parallel, no vortex there, but vorticity is not 0. Okay. So, although streamlines are parallel, omega is not equal to 0, vorticity is not equal to 0. I think that is something which I want you to remember. Okay. So, the only way you can find out if a flow field is irrotational or not is by calculating the curl of V. If the curl of V is 0, then you can go for irrotationality, then you can try to find the potential function. Otherwise, you will not be able to find the potential function. That is the reason I kept saying phi, if phi exists, phi will exist only if it is irrotational, not for rotational. So, what I want to summarize is, for 2D flows, psi exists. Okay, you can define a stream function, and it satisfies the equation of continuity, but if in addition flow is irrotational, then del square psi, which is equal to omega, must be equal to 0, because it is irrotational, omega has to be 0, omega is curl of V. Okay. And you can see in the earlier example, psi was y square, u naught y squared. So, psi is u naught y squared by 2, I think. So, clearly d square psi by dy squared is equal to u naught not 0. Point is, for irrotational flow fields, del square psi which is omega must be 0. If flow is 3D, phi can be defined. Okay. So, that is the difference, psi is only for 2D, phi can be for 3D, but again it has to be irrotational, but flow has to be irrotational. So, basically what this means is V is equal to gradient of phi. Okay, this is a vector. So, if I have 3-dimensional flows, I can always, and if it is irrotational, I can define a potential function. Velocity is equal to gradient of phi, and from continuity divergence of V del square phi equals 0. V must satisfy the continuity equation, V is gradient of phi. So, phi has to satisfy the Laplace. So, the Laplacian equation, let us say we stick to 2D flows. Laplacian equation is satisfied by both stream function and potential function if it is irrotational. Okay. If the flow is irrotational, both are satisfied, both satisfy the Laplace equation. So, then you will say I should get the same solution. clearly you do not get the same solution. The reason is the boundary conditions to which you are going to subject them are going to be different. Okay. The differential equation is the same, but the boundary conditions are different, which is why psi and phi are different. Okay. So for 2D irrotational flows, both for 2D irrotational flows, del square psi equals del square phi equals 0. The boundary conditions are different. Okay. I just thought I should make you understand this, and solving a few problems usually helps. Okay. Now, in the morning what we saw was some application of dimensionless analysis. I want to continue that and talk about another problem. Okay. And this problem is one which is called the lubrication approximation. So, this lubrication approximation usually arises when problems have two different length scales. So, if there is a problem where the length scale in one direction is different from the length scale in the other direction, then you will possibly scale in each direction using the appropriate length scale. Okay. So, these kinds of problems can result in some simplifications, okay, and you can get some insights. So, that is what we are going to look at, and the usual problem is that of flow between, let us say this wall is stationary, y equals 0, this is x direction, this is the y direction, this is y equal to 0, and let us say u is equal to 0 here, and I have y is equal to h of x. This is a wall, okay, which is also a solid wall, but it is not y equal to constant. Idea is this, the length scale in the y direction is h, the length scale in the x direction is L. Okay. So, this is very and let us look at the problem of, let us say, cuvette flow, where one wall is moving past the other wall. If the two walls are stationary, then you know the profile which we got, the linear profile. But now, because this is a diverging wall, you are going to have a situation where the velocity is going to change in the direction of the flow. Okay. So, dvx by dx is not going to be 0, because the gap between the, so earlier we said we had assumed fully developed flow, we said the velocity is not going to change, but now I cannot make that assumption that the velocity does not change. So, fully developed flow assumption is going to break down, it is not going to be valid, because clearly the velocity here is going to be high, the velocity here is going to be low because the gap is high. Okay. So, there is going to be no question of having a fully developed flow. So, now we want to analyze this problem and see what kind of scales we have to choose for making this dimensionless. So, where do these problems arise? Supposing you have a cylindrical shaft which is rotating in some housing, okay, the gap between the shaft and the housing will change as it moves, okay, because you have, let us say, a cylinder which is moving around and let us say a flat plate. So, clearly this gap here, because this is circular, the gap between this wall and this wall is going to keep changing, it is not flow between flat plates. Okay. So, in these kinds of problems we want to figure out what are the kind of stresses, forces that are going to arise. So, this is one of the classical examples where a lubrication approximation is used. So, my point is this is small, this is large, and so that is an example of how the gap, the liquid is flowing between a very thin, like lubrication of the oil or very viscous liquid you put, okay, between a bearing and a housing. So this is what you get. So the gap between the two surfaces changes, because this guy I have kept it flat, that is circular. So clearly now what I want to do is, let us say one of these vessels, this wall is moving at a velocity u naught, okay, u characteristic, u is the characteristic velocity in the x direction, and let us say one of the walls is moving at this velocity u, that is in the x direction. So the characteristic velocity in x direction is u characteristic. Now the x characteristic is going to be L, the y characteristic is going to be h, the gap between the two plates, okay. So in this direction the characteristic height is, length scale is h, in this direction the characteristic length scale is L. Now what do I get? I want to make sure I do not know what the characteristic velocity is in the y direction. I know that it is non-zero, because in the from equation of continuity, du by dx plus dv by dy equals 0, du by dx is not 0 because it is not fully developed. So dv by dy will be non-zero, so dv by dy will exist. I want to know what is the magnitude. Intuitively what do we expect? That the dominant component of velocity will be in the x direction, the component in the y direction will be very negligible, right. So that is what we expect. So how do I infer that mathematically? By looking at the equation of continuity. So I have not told you what the characteristic velocity is in the y direction, okay, the v characteristic. But so I am going to make this equation dimensionless, and I am going to say u naught x is made dimensionless by L du star by dx star, okay. What is this, like we did earlier, u star is u divided by u naught, okay, x star is x divided by L, y star is y divided by h, okay. And now, so I am just substituting for u as u naught multiplied by u star, x as L multiplied by x star, and these are constants, so I can take it out of the derivative. I do not know what the v characteristic is, but I know the s characteristic is this, star by dy star equals 0, okay. This is what I get. So now I want the two terms in the continuity equation to contribute in the dimensionless form. I told you when I am making it dimensionless, I want to make sure that both the terms are of the same order of magnitude and they contribute, okay. So I want this to be of order 1, this to be of order 1, same order of magnitude. If both of them are going to contribute, they will be able to balance each other only if the characteristic velocity in the y direction, v characteristic by h is equal to u naught by L, okay. So v characteristic by L must be equal to u naught by h. So v characteristic is h by L times u naught. So the characteristic velocity in the y direction is, you know, epsilon times u naught, where epsilon is h divided by L. I told you two length scales are completely different, h is very small compared to L, okay. The gap is much small compared to the radius of that circle that I drew, okay. I drew both comparable so I could see it properly, but the gap will be very small. So from this we basically conclude that the velocities in this direction, in the transverse direction to the flow, are negligibly small, Okay. So, that is the inference, and this is the right. Only if I choose weak characteristic like this, my momentum, my equation of dimensionless equation of continuity will be this. So, this choice of weak characteristic ensures this, and my two terms balance. Okay. So, now I want to just directly jump to the x momentum equation and see what inference I can make. Okay. So, I have neglected the gravity term because I can absorb it in pressure like we discussed in the morning. So, this is the x momentum equation. Okay. I am going to make this dimensionless now using the characteristic scales for x and y and u and v that we already obtained. Time I will just make it dimensionless using L by u. Okay. T characteristic is L by u. So, now I would get let me go there. So, I write this as rho times du star by dt star, and this will give me one u. T star, T characteristic is L by u. So, I get an L. So, this gives me u squared by L, okay, plus u is going to give me, did I use u naught last time? Did I use u naught or capital U? U naught. Yeah, let me make it u naught because my capital U and small u look the same. Okay, u naught comes here, and one more u naught comes here, one L comes here. So, I get u naught squared by L plus again V characteristic comes out, but V characteristic is nothing but we got something here h by L u naught. Okay. So, it is h by L u naught multiplied by V star times du star, that gives me one more u naught, and I get dy star which gives me another h. So, this is coming from this h u naught by L comes from making V dimensionless, this is V characteristic. This h comes because y has been converted to y star, and this comes because u star has been made u naught. Okay. This is equal to minus P characteristic dP star by dx star by L plus mu times d square u star by dx star squared plus d square u star by dy star squared. This 2 will give me a u naught here, this will give me a L square at the bottom, this will give me an h square at the bottom. Okay. By making it dimensionless. So, that is what we have. You see, in all of these terms I have u naught squared by L common because this h cancels off. Okay. So, I can write this as rho u naught squared by L, and instead of writing 3 terms every time, I am going to write it as a substantial derivative capital D, which we did long ago. So, I am going to write this as d dt of u star. Okay. d dt of u star is nothing but these 3 terms with all the stars, and the rho u naught squared by L is taken out, it is occurring in all the terms. Then I can write this as minus PCH by L dP star by dx star plus mu u naught. What I want to do is I want to write factor out h squared common from both, okay. So I am going to write this as h squared, and then I have h squared by L squared d squared u star by dx star squared plus d square u star by dy star squared. Okay. What I have done is just taken h squared common. So I get h squared by L squared. Again we invoke the fact that h by L is very small, okay. So compared to these two derivatives, this guy will be, this is epsilon squared, so this is very small, okay, and I can neglect this in comparison to this. So I have rho by L equals, I still have not told you what is peak characteristic, minus peak characteristic by L dp star by dx star plus mu u naught divided by h squared times d square u star by dy star squared. Now what I like to do, since I have an h, I have an L, I like to write everything in terms of L. And so h is epsilon L, okay. So I am going to write this as minus p characteristic by L dp star by dx star plus mu u naught by epsilon squared L squared d square u star by d y star squared. Again I have not yet chosen the pressure characteristic, the characteristic scale for pressure, okay. I need to therefore now decide what I want to do. I can multiply these equations throughout by this guy here, epsilon squared L squared mu u naught, okay, multiply by epsilon squared L squared by mu u naught, this entire equation, okay. What do I get? If I multiply this equation by this, I will get epsilon squared rho u naught L by mu times d dt of u star equals minus PCH times L by mu u naught times epsilon squared times dp star by dx star plus d square u star by dx star squared. That is what I got. All I have done is I have taken the this term, multiplied it by the reciprocal. So this coefficient becomes 1, okay, this coefficient becomes 1, and this is what I get. So see, in my flow, in this problem of the lubrication approximation, where there is a flow between two not parallel plates, slightly inclined plates, I need to have a balance between forces. These, so the question is, the way I have chosen my, I can choose my pressure characteristic, okay, to be, I want this term, the pressure term, which is going to develop because of this flow, to balance my viscous term. That is one option that I have. So if I choose my P characteristic is chosen as mu u naught by L epsilon squared, I will have epsilon squared multiplied by Reynolds number multiplied by du star by dt star, that is this term, this is a Reynolds number, equals minus dp star by dx star plus d square u star by dy star squared. This will become 1. I have chosen this peak characteristic, so this becomes 1. So, now these two terms will balance each other. For low epsilon, this is 0 for low epsilon. So, if your characteristic scales are so different, H and L are so different, okay, what this means is the pressure forces are going to balance the viscous forces, but the characteristic pressure is going to be very, very large. A very large pressure is developed in this gap between the two plates, and this gap is what is basically helping you bear the load. Okay. I think I wanted to do this scaling analysis to just show you that the gap, the small deviation in the gap between the plates, which is and the difference in the length scales gives rise to a large pressure. If I do not include epsilon square, then this term will also disappear. If I choose my peak characteristic without the epsilon square, then this will also be of order epsilon square. So, then it will be viscous force equal to 0, that does not make sense. So, the viscous force has to be balanced by something. Okay. So, that is the moral of the story here. Okay.